When you think of complex engineering systems, you might think that there'll be very complex ways that you need to calculate the area or perimeter or volume of systems. But you'll be surprised to see when we're actually analyzing systems, most of the time you're just looking at squares, circles, and triangles. Sometimes that's a result of it's a lot easier to make these basic shapes from a manufacturing perspective. Other times, from an analysis perspective, assuming certain shapes are approximately a circle, a square, a rectangle, or a triangle is good enough. And the added cost of the complexity, not just calculating the area or perimeter, but calculating the properties because of that more complex shape is not worth it. And so we make assumptions a lot of times. So we're going to look at some of these basic shapes, review what the area and perimeters are, and think about the principles of how those were even determined so that when you do need to look at a more complex system, you can justify simplifying it because the area is a certain percentage off only and you don't care that much. But understanding the properties that are affected by the area or perimeter are also important in dictating what assumptions are appropriate. So our first basic shape is a rectangle. And when we think of the rectangle, we are given a length and a height. Sometimes this is described as your width, but you have two length scales, right? The rectangle has four right angles and two parallel set of edges that are of the same size, right? So this side and this side are the same, this side and this side are the same. And so we say that if you just multiply these two length scales, then we get the area of this rectangle. So just to graphically represent this, if we think of a unit cell with 1 by 1, whatever the units are, right? And I show a white circle and a red circle so we can actually more easily distinguish it. And if I place them on here, and I have 20 in this direction and 50 in this direction, you can add them up, but that's basically the definition of multiplication, right? So that's how you probably learn why multiplication works. It's just grouping. Whether you look at it from a column by column perspective or a row by row perspective, it's the same thing. So in this case, 20 times 50 gives us 1,000. If these were in inches, the units would also multiply. So then this would be 1,000 inches squared, or meters squared, or feet squared. Depends on what the units are. The perimeter. So the area is the shaded space within your shape. The perimeter is the sum of the edge components. So think if I want to build a fence around this this lawn, let's say, what's the length of fence that I would need to satisfy this? Well, you have two sides that are h length, so 2 times h, and two sides that are l length, so 2 times l. So 2h plus 2l, or 2 times h plus l. For a rectangle or square, it would be the same thing. So in this case, this will be 140, and in this case, you're just adding the length scales or the units. So this will be in inches or meters, whereas the area will be in length scale squared. Okay? How about for a triangle? Well, if we know for a rectangle, we can use that to help us understand what it would be like for a triangle. So let's take a look at this rectangle. I have a height. A lot of times for triangles, we redefine this as a base, but we can also call this our length, as long as we're clearly defining what we're looking at. And if I draw a line across these corners, right? I split this rectangle directly in half. This triangle has a height of h and a length of l. If this was a full rectangle, I know that I would just need to multiply length and the height, and I will get this full triangle or full rectangles area. If I cut it in half, each of these triangles has an area half of that full rectangle. So this can be written as 1/2 the height times the length, or height times base. Okay. But you might say, well, this is a right triangle. So does this work if my triangle is not a right triangle? So let's take a look at a case where you don't have a right triangle, right? As we see here. So we have our height and we have our length component here. So I don't have a right triangle, so I can't as easily see that this is half of the area of h times L. But if I cut this, so I do have two right triangles. They're not of the same size, but I can look at each of these individually, right? I can find the area here and then find the area separately here and add them together. Well, this component is just like this. The length is not L, it'll be L minus whatever this length is here. But I see I would get part of a rectangle there from this half. I see the same thing over here. So if I look at this total rectangle, and that would be h times L, that's the area of that total rectangle, and I see 1/2 is here and 1/2 is here. So if I divide by 2, I also get the area of the triangle. So it works for this equation works for any triangle, as long as you are clear what you're defining as your height and your length, right? So the height from one corner normal to another side, and then one of the sides being flat. And we can calculate it for this case here, 3.15 inches squared, right? Because it's an area, it will be in square inches, because I defined the units here. If I want to find the perimeter of a right triangle, it would be this length plus this length plus this diagonal length, right? So right here we have our height h. Right here we have our length L. Because we're specifically looking at for a right triangle, this we can apply Pythagorean theorem. H squared plus L squared would equal this length, this diagonal squared. So if I just want the diagonal, I'll take the square root of that and we can solve for it. If you have something that's not a right triangle, you can break it up, and all it is this length plus this length plus this length here. Okay, so let's take a look at two more shapes, and it really captures a lot of the different shapes that you will see. So here we have a combination of the rectangle and triangle, right? We have an isosceles trapezoid. So we got two parallel length scales here, and we're saying that this length and this length are of equal lengths. Okay, so we have the height from this corner drawn down with a normal line to the bottom length. Sometimes you'll see these defined as like base A and base B, or but in this case I'll just keep it as length 1 and length 2. Okay, so the way to think about this trapezoid is to break it up into the triangles, right? So I got one triangle there, and a rectangle here. Okay, so if I look at it from that perspective, I can break up into how does this compare to that full full system. So if I break it up into each of the individual shapes, we can look at that first. So I can look at each of the triangles using this equation here. So the height, so the area of a triangle is 1/2 height times base, right? So if I just look at this triangle, let's say this red triangle right here, it'd be 1/2 h times this length. And what is this length? This length is L1 minus L2. And that would be this length plus this length. So divide by 2. So L1 plus L2 divided by 2 gives me this one length. That's what this term is right here. Times h would give me this full rectangle right here. If I only want to look for this triangle, I'll take 1/2 of that. But because I have two of these triangles that are equal, I'll just say h times L1 minus L2 over 2. Then we need to add this rectangle here, plus the height h times this length is L2. It's already given to us. So if I clean this equation up a little bit, I get the height times L1 over L2 minus L2 over 2 plus L2. right? And L2 minus L2 over 2 just could be L2 plus 2. So this we can simplify as area is equal to the height times L1 plus L2 over 2. If I look at this full system, this triangle basically can be stacked right there, right? And so that basically is the height times this length right here. Well, this length right here is basically the average, or L1 plus L2 divided by 2, the average of these two lengths components. That's what this term is right there, right? So either way, I like looking at it from a triangle perspective, setting up this way first. So you could build very complex systems by breaking up into triangles, similar to what we looked at in the previous video. Now, the last shape that we have not talked about is the circle. Oh, before I go there, the perimeter of an isosceles trapezoid. Similar to how we looked at it for rectangle and triangles, we have L1 plus L2, right? The outer, or sorry, the base length components. And then we need to know these diagonal components. Sometimes that's going to be given to you, sometimes that's something you can measure, and if not, you can still calculate it for this isosceles trapezoid. This will be 2 times the length of one of these, and you can look at this from Pythagorean theorem, looking at these triangles. So what is the length of this component right here? We said earlier, L1 minus L2 over 2. So that squared plus h squared would equal this diagonal squared. So we take the square root of that, and that's what we have right there. Okay, so now let's take a look at the circle. So we know that if we look at a circle, we can define the diameter or the radius. We're going to look first at the radius, and we can define the area of the circle as pi r squared. Now, if I draw a square around this, where the edges touch a single point, right? These 4 points on the circle, right? So these sides are tangent to my square. That's the smallest square that this circle can fit in. Okay, so this area is pi r squared. Pi is about 3.14, so it's about 3.14 times r squared. If I try to find the area of this square, right, this entire square, not just the blue shaded parts, I would expect the area of this square to be larger than that of the circle because the circle fits inside it, right? So the diameter is 2 times the radius. So from the previous slide, we know that the area of a circle or a square or rectangle is the height times the length. In this case, because it's a square, it would just be the diameter or the length squared, right? So 2r squared. So that's equal to 4r squared. 4r squared is larger than 3.14r squared. So at least from that perspective, we know that, what am I trying to say? We know that it's conceptually the trend that we expect. Now, you have 4r squared and you subtract it by pi r squared, then you would have the area of these blue shaded areas. And if you divide that by 4, you can have one of these shaded areas. So you can see how combining known area terms can simplify and help you solve for different geometries that we're not specifically talking about, different shapes we're not specifically talking about. Now, perimeter of a circle. Perimeter of a circle is the same thing as a circumference. This can be defined as 2 pi r, or pi times the diameter, because diameter is 2r, right? So that's the length that you would need wrapping around this circle. We can see from the square, since the circle fits inside the square, you would expect the perimeter of this square to be larger. All right, so let's check. We have the diameter is equal to 2r. If I want to find the perimeter, I would just need to add it 1, 2, 3, 4 times. So 4 times the diameter would be the perimeter of this outer square. Pi times the diameter is the length of, or the circumference of this circle. 4 times diameter is larger than 3.14 times diameter. So again, from that perspective, it makes sense. The scaling makes sense, at least. All right. So in future videos, we can take a look at volume, and then we have surface area and cross-sectional area. So we can start taking a look at three-dimensional objects and breaking it down into components that look like circles, trapezoids, squares or rectangles, and triangles. You'll be surprised how often these are the basic shapes that show up in your classes, and when you're making assumptions in real-world systems, that these are appropriate a lot of the time.